Welcome. This is 48L video 2, and we're going to start off talking about torque. So torque is the angular equivalent of force. It's what you get when you apply a force out of line with a hinge or a turning axis. When you push open a door, you're applying a force away from the hinge, and so the door turns. So it's the turning effect caused by a force that's not in line with a hinge. A tendency of a force to rotate an object about some turning axis is measured by a vector quantity. This is actually a vector quantity. It has a magnitude. It's got a symbol, which is tau, and it has a magnitude, which is given by the size of the force, the size of the distance to the turning axis, and the sine of the angle between those two. So here's an illustration. We have some kind of turning axis, and we have a lever around it, and I'm applying the force at some angle. And what I do to figure out the torque is I take the component of the angle of the force that's perpendicular to the distance, what we call the lever arm, or I take the component of the lever arm that's perpendicular to the force. And it turns out either way I get the same answer, because if I look at this, this is F sine theta, and this is R. So I have F sine theta times R. And if I look at the yellow version, I have R sine theta, and this is F. So either way I get the same magnitude. Okay, so if it moves that way, so if a torque tends to cause a counterclockwise motion, we call it a positive torque. And if the torque tends to cause a clockwise direction, we call it a negative torque. The vector is actually at 90 degrees to the plane of this circular motion. So if we use the analogy of a door, if you push a door open, so you push it away from you, and the hinge is on the left hand side. Let me draw an illustration here. If I have a door and the handle is here on the right hand side and the hinges are here on the left hand side, if you push this door away from you, you will cause a torque which is pointing upwards through the hinges. And if you pull the door towards you, you'll cause a torque which is pointing downwards through the hinges. So it's unusual to think about this as being a vector, but it is a vector. The relationship between torque and angular acceleration, we can say F equals ma. We can also say torque equals moment of inertia times alpha. Let's look at these questions. We can say determine the torque about axis O. Here's my axis O, caused by force F. There's a force up here, and I'm going to say, well, my torque is equal to the force times the displacement of the force from the turning axis times the sine of the angle between them. It's a bit like work, isn't it? Work is equal to the force times the displacement of the force, and it was the cosine of the angle between. You wanted the maximum when the force was in line with the displacement, and you wanted zero work when the force was at 90 degrees to the displacement. With torque, it's the opposite. With torque, we have torque is equal to the force times the displacement times the sine of the angle between them. We want the maximum torque when the force is at 90 degrees to the displacement, and we want zero torque when the force is in line with the displacement. So although they use the same symbols, you know, and the equations are similar, then they're not the same by any means. So torque is equal to the magnitude of the force times the magnitude of the displacement times the sine of the angle between them. So in this case, it's going to be 7 times 3 times the sine of 60. So this is going to be equal to 21 sine 60. So my torque is going to equal 21 sine 60, and my torque is 18.19. 18.19 Newton meters. Look at the units. Look at the equation. Newton meters. Make sure, of course, that your sine was in degrees, because what I gave you was in degrees. Okay. A solid cylinder has a radius of 2 meters and is rotated about its turning axis 0 by a tangential force of 7 newtons. So here's my 7 Newton force. Here's my 7 Newton force. And here's my turning axis. And this is a tangential force. The way you do that is you wrap a rope around the drum and you pull on the rope, and it always forms a tangential force. It's a nice trick. The moment of inertia of the cylinder about the turning axis is 6 kilogram meter squared. We'll get to this later, but that's your rotational mass. It's the amount of inertia you have caused by this mass and its position. And then what is the torque about the turning axis caused by this force? So what is the torque about this turning axis? Well, the torque is the turning effect, which is torque is equal to the force times the displacement, what we call the lever arm, times the sine of the angle between them. And if I look at my diagram, my lever arm is there and my force is there, and there's 90 degrees between them because I wrapped a rope around, and it says it's tangential. So this is equal to 7 times the distance is 2 meters times the sine of 90, which is of course 1. So this is going to be 14 Newton meters. So then the next question is, what is the angular acceleration of the cylinder about this turning axis? So I say, well, what do I know? I know my torque is equal to 14 Newton meters. What else do I know? I know my moment of inertia was given to me as 6 kilogram meter squared. And it's asking me for my alpha. And I say, oh yeah, torque is equal to I alpha, just like F equals ma. So 14 is equal to 6 times alpha. So alpha is equal to 14 over 6, which equals, I guess, 2.33. It's going to be radians per second squared. So there we have it. Let's have a look at this next page. So here we're looking at moment of inertia. It's the inertia around a turning axis, and I can think of it here as here's a mass. It's connected somehow to a turning axis and it's revolving around. And we say, well, what's its inertial effect? It's going to cause a reluctance to angularly accelerate. It's going to try and continue going at the same angular velocity unless we do something to it. How do we find it? And it turns out that the moment of inertia for a discrete particle, for a particle by itself, is equal to, well, the mass of the particle times its distance from the turning axis squared. What that means is, if I move a mass twice as far away from the turning axis, it's 4 times more reluctant to rotate. So if you want to make yourself rotationally more stable, it's easier to move the mass away than it is to try and get more mass. You see this actually in day-to-day life. People intuitively do it. If you're actually walking on a wall, not that I suggest you do, but if you're walking on a wall, what people do is they put their hands up. What they've done is they've taken this mass which was down here and they've moved it up and made themselves more stable. Tightrope walkers, not only do they walk a tightrope, they carry a big rod with them. Well, yeah, they moved mass a certain distance from the turning axis, and if they get into trouble, they hold it up and it makes them really quite stable. So we intuitively know that if you want to stop yourself from rotating off something, you move mass further away from the turning axis. We intuitively know this, but this is the mathematics of it. If I have more than one mass, of course, I get the sum of these. That's fair enough. It turns out that if I get conglomerations of masses, I form structures, then I can get set equations for these, and there's 3 of them that it's useful to know. There's the moment of inertia for a hollow hoop. You might think of a hollow hoop as being a piece of pipe. It's hollow, it's circular on the outside, it's hollow, or a washer. I don't use those terms in questions. I call it a hollow hoop so there's no misunderstanding. And that would be mr squared. It would be the mass of the object times the radius squared. That would give you the moment of inertia. If I had the moment of inertia of a solid cylinder, you might think of that as a bar, a solid bar of material. Or you might think of it as a disc, like a compact. Well, we don't see compact discs anymore, but a washer, a coin, something like that. I don't call them those things. I call them a solid cylinder, so there's no confusion. It's a half mr squared. It's a half the moment of inertia of a hollow hoop. And if I take a solid sphere, a ball, then it's 2/5 of mr squared. So we learned those. Those are the ones I expect you to know. There's others, but those are the ones I expect you to know. And then the final thing we talk about is if I have a distributed mass revolving about an axis, then I can actually work out its moment of inertia about that axis by using an integral. If this was a summation, this is an integral of r squared dm. We've done this kind of thing before. So that's where we're going to go. Let's look at some examples. So we have determined the moment of inertia about the origin of this system. So there's 3 masses. There's a 4 kilogram mass, a 5 kilogram mass, and a 3 kilogram mass. And if I recall, then the equation said the moment of inertia was equal to the sum of each mass times its distance from the turning axis squared. So this is a case of figuring these things out. Let's take the 4 kilograms. So it's the 4, and that distance is 3. It doesn't matter, the direction is completely irrelevant. It's just it's 3 units away, so it's 3 squared. And then if I take the 5 kilogram mass, and this is 2 units away, so that would be 2 squared, and then I take the 3 kilogram mass. Now I'm making us work a little bit for this. There's the distance that I want, and I know that this is 3 on the base and 4 on the side, and I recognize a 3, 4, 5 triangle, so that's 5 squared. If you didn't recognize that this was a distance of 5, you could get it by Pythagoras and simply say, you know, this distance squared equals 3 squared plus 4 squared, which is that distance squared equals 25, so that distance is the square root of 25, which is 5. So we have I is equal to 4 nines plus 5 times 4 plus 3 times 25. I sometimes do those steps in my head, but I try not to, because for checking the work it makes it very convenient to have it all written out. 3 nines are 27, 4 nines are 36, plus 5 fours are 20, plus 75, which equals 95, 131. And the units, well, look at the equation. Kilogram meter squared. 131 kilogram meter squared. Just as an interest, this one that's 5 meters away, it's not even the heaviest mass, it's the lightest mass, but it's the longest distance, and that gives us 75 units. This one here, which is the shortest distance but as the heaviest mass, gives us, that's going to be the gives us only 20. It's the heaviest mass, but it's the shortest distance. So moving away makes a huge difference. A solid sphere has a radius of 4 meters. So let's visualize this as my solid sphere, and it's got a radius of 4 meters, and its mass is 2 kilograms. What is its moment of inertia about its circular axis? The circular axis is that axis there. And we say, well, about that axis, I happen to know that the moment of inertia of a solid cylinder equals 1/2 mr squared. So my moment of inertia about a solid cylinder is 1/2 times 2 times 4 squared, which equals 16 kilogram meter squared. Just by the by, this object, any object, is if you like, an infinite number of moments of inertia, because I could choose an axis through there, or an axis that's coming out here, or an axis through there, or an axis that's coming out there. That moment of inertia changes about each of those individual axes. We tend to focus on the axes that are the center of the circular symmetry, but we don't, life doesn't have to. So let's look at our next problem. Our next problem says, using the method of calculus that was shown in physics class, show that the moment of inertia of a solid cylinder about its circular axis through its circular center is 1/2 mv squared. So now we're asking to prove this, and this is not an uncommon question. So let's do it. We've done a few integrations before, so this is like the next step. I'm going to set myself up a little bit. So first of all, let's have a radius, and I'm call this radius big R. And we have a mass, and we'll call this big M. And then we'll have a thickness, and let's call that T. And I know that for something like this, my moment of inertia is equal to the integral of R squared dm. So I don't know how to do that. How do I do the integration of R squared with respect to dm? I have to do the conversion. So I say to myself, well, okay, I have an R value, that's where my slice is, and I have a width to my slice, which is dr, and I think I'm off to the races. What I say is, I say the little bit of mass which is in this sleeve. Remember what we do? We take a sleeve and we integrate it from the smallest sleeve near the middle to the biggest sleeve near the outside. So at this arbitrary position, my little bit of mass is equal to, well, it's going to be the volume mass density times the volume of the sleeve. So my dm, my little bit of mass, is equal to, well, my volume mass density is the total volume, the total mass, I'm sorry, divided by the total volume, which is pi r squared, that's the front face, times t, that's the depth. It's that times the volume of the sleeve. And the volume of the sleeve, imagine taking this sleeve out and cutting it and unrolling it. And what we see is that the volume of the sleeve, well, there's a circumference, that's 2 pi r, little r of course, not big R. And then there's a little width, dr, and then there's a thickness, t. So visualize it and it falls into place. My thickness cancels with my thickness, my pi cancels with my pi, and that's about it. So I can say this equals 2m r dr over r squared. I think that's everything. I'm just working my way through it. I think that's fine. So I can substitute this back up here. And I say I is equal to the integral of r squared. And rather than putting dm down, I'm going to put down 2 big M r dr over big R squared. Let's take out all the constants. Well, 2 is a constant and the mass of the system is a constant, and big R, the radius of the system, is a constant, and that leaves my integral of r cubed dr. So I is equal to 2m over r squared, and this is going to be r to the 4th over 4, and my limits, the smallest sleeve has 0 and the biggest sleeve would be r meters away. So I is equal to 2m over r squared, r to the 4th over 4 minus 0 to the 4th over 4. So I is equal to 2m over r squared, r to the 4th over 4. So I is equal to the 2 and the 4 makes 1/2. M is left and r squared is left. So we proved one of those equations. It's the easier one to prove. You can do the same thing for the sphere and you can do the same thing for the hollow hoop, but this is the easier one to prove. So there it is. We're using some maths to prove an equation that we're using. So there we have it. Let's end this tape now.